So good evening everybody. Legacy of the Hubble Space Telescope. As you can see from the subtitle, I'm going to be talking about how it went from being a white elephant to a white knight. And there can be very few people who don't recognise the iconic form of the Hubble Space Telescope, not just astronomers. I would reckon that if you passed a man in the street, then you would find that if you show them this picture, they will all recognise the telescope. So what I'm going to be talking about this evening is looking at an introduction to why we need space telescopes and ground-based alternatives. I'll be looking a little bit about why the mirror was flawed and how the optics were fixed, and then looking at the legacy in terms of what the Hubble Space Telescope has done for our understanding of the universe and how the public came along for the ride. And then before finishing, I'll just revisit this idea of, do we still need space telescopes despite the ground-based alternatives? So this is a good way of just summarising all of the various telescopes that are around. It doesn't cover the very early ones, but it gives you an idea of the relative sizes of lots of telescopes that exist at the moment. All the way from the top left here, you can see the 1 metre or 40-inch Yerkes Observatory objective lens. And towards the right, some of the telescopes that will be coming online shortly, such as the 30-metre telescope in Hawaii and the 40-metre European Extremely Large Telescope. By comparison, space telescopes have got very small mirrors. If you look down in the bottom left, you will see 4 space telescopes. The Hubble that I'm talking about this evening, plus 3 other space telescopes which I'll make brief mention of towards the end of the talk. Gaia, Kepler and the James Webb Space Telescope. So you can see by comparison the size of the Hubble Space Telescope with a mirror diameter of 2.4 meters is tiny by comparison with the largest telescope in the world at the moment, up here in yellow, the Gran Telescopio Canarias on the Canary Islands. That's the largest at the present, and within a few years we're going to have these monster telescopes coming online. So you can ask, why do we bother with such a small telescope? Well, remember why we keep pushing for larger telescopes. Telescopes have come, of course, an awful long way in the 400 years since Galileo. Refractors using lenses have given way to reflectors using mirrors. Since we reached a lens diameter of about 1 metre, lenses became impractical, and so telescopes switched over to using mirrors. But the quest for larger telescopes or larger mirrors has been driven by 2 principal factors. Larger mirrors mean that we can collect more light, so we can see fainter objects, and the larger mirrors also give rise to higher resolution, so we can see more detail, which means we can either see smaller objects at the same distance, or we can see similar objects at greater distance because of that higher resolution. So going to larger and larger apertures gives us a double whammy of more light and more detail. So if we have all of these huge telescopes on the ground with even larger ones coming online soon, then why do we put a small telescope like the Hubble into Earth orbit? And I'm sure you realise the reason is because, of course, we want to get above the Earth's atmosphere. The Earth's atmosphere is essentially transparent, but it does produce turbulence, it does produce the shimmering of the stars, and hence can obscure detail that we would otherwise see with a mirror of a given diameter. And so if we compare, for instance, a mirror or a telescope with the size of the Hubble mirror of 2.4, if we compare its performance on the ground or even on the top of a mountain compared to its performance when in orbit, there's a factor of about times 10. In other words, the resolution is some 10 times better than we could achieve with the same size telescope sitting on top of a mountain somewhere in the world. So a huge increase in resolution, even if it collects the same amount of light. So it's well worth having, and arguably it's well worth the expense of putting a telescope in orbit in order to achieve that, to get away from the limiting effects of the Earth's atmosphere. So let's think about the history and the timeline of how the Hubble Space Telescope came to be. The idea first started in the 60s, perhaps earlier than you thought, and in 1970 NASA started making serious plans for what they called at the time a Large Space Telescope, the LST. That was the first milestone, putting forward a plan as to how that might look. I'm not sure you know what the second milestone might be. The second milestone was, it was cancelled. Congress withdrew funding, saying, great idea guys, to NASA and the scientists and the astronomers who wanted this telescope, but Congress said, great idea, but we can't afford it, way too expensive. So a whole load of scientists and astronomers then got very uppity and started to lobby senators, and eventually it was agreed that, well, okay, maybe we need to look for more funding. So NASA, or America, approached ESA and said, can we collaborate on this? And eventually it was agreed that if a lot of the money came from NASA, but some of the money came from ESA, then it would just about be an affordable project. So in 1978, Congress agreed the funding of the LST project. And at that point, the task of building the Large Space Telescope was put out to tender. The spacecraft construction went to Lockheed, and the optical tube assembly went to Perkin-Elmer. Now, we as astronomers tend to think of the Hubble Space Telescope simply as a telescope that happens to be up there. But NASA and ESA actually treat it as a spacecraft, and it's a spacecraft that happens to have a telescope inside it. So it's a slightly different point of view. But in terms of manufacture, those two things had to be separated. The idea of building a spacecraft with the solar panels, the power systems, etc., the gyroscopes to make sure we could point in the right direction, separately from who is going to build the optics that are going to go inside this spacecraft. So Perkin-Elmer and Lockheed were given the prime contractual jobs of building the LST. In 1979, the construction of the primary mirror began. So there's Perkin-Elmer engineers, having spent something like a couple of years making the mirror, grinding the mirror, polishing the mirror and coating the mirror. That took about a couple of years or so. Rather less than some of the other projects that you might have heard of, because mirrors that are 8 or 10 or more meters in diameter will take longer. But remember, this is not the largest mirror ever made. 2.4 meters is relatively modest. Even by 1979 standards, it was relatively modest size. But after 2 years, it was declared complete, and it was declared essentially perfect in terms of testing to make sure that the mirror was as smooth as it could possibly be. Congress and ESA, I guess, also realised that construction of the primary mirror was absolutely crucial to the project, such as a space telescope. If you get the primary mirror wrong, of course, that is absolutely catastrophic. So they said, just in case there are any difficulties with Perkin-Elmer making a primary mirror, we're going to have a second manufacturer make one in parallel. So it was agreed that Kodak would make a duplicate mirror. But in 1981, when Perkin-Elmer said, we've made our mirror, we've tested it, and it's fine, at that point, work on the Kodak mirror, the backup mirror, was halted because there was no need for it anymore. Perkin-Elmer had delivered on their mirror, and the Kodak mirror was effectively halted. They didn't bother coating it with aluminium. They simply said, well, we made the mirror, it's been tested, it looks okay, but we don't need it, so the Kodak mirror went into a museum. And that, of course, is relevant for a little later in the story. 1983 was the original planned launch date, and at that point the Large Space Telescope was actually named the Hubble Space Telescope, of course in honour of Edwin Hubble, who had done a lot of work on the Hooker and later the Hale telescope, looking at recession velocities of galaxies to establish the expansion rate of the universe. There were then a few delays. 1984, the launch date was put back due to a few scheduling slips on the part of Perkin-Elmer, and then the launch date was put back again because Perkin-Elmer and Lockheed had a few problems. By 1986, the budget had hit something like $1 billion, and it was still rising. And of course that date lives in a lot of people's memories, because 1986 was the date of the Challenger disaster, which meant that all of the shuttle fleet were grounded for a few years before they finally resumed taking satellites back into orbit. There was then a large backlog of people who wanted their objects, including the military, launched into orbit. So the Hubble Space Telescope didn't finally make it into the launch list until 1980, when it was finally launched. By that time, the construction costs were an estimated $2.5 billion. This doesn't count the cost of any future shuttle launches to maintain the Hubble Space Telescope. So a very expensive telescope, but it was considered worth it in order to get above the Earth's atmosphere. Excuse me. Before going any further, it's worth saying just a little bit about the design, and that is that the Hubble Space Telescope has a particular design called a Ritchie-Chrétien design. Excuse me. So some of you might be familiar with the Ritchie-Chrétien design. It means that instead of having a parabolic mirror to focus light from a distant source, it uses a primary mirror which is hyperbolic, a similar shape but not quite the same. It's still a conic section. If you take a cone and slice it in particular directions, you get a circle or an ellipse or a parabola or a hyperbola. All we need worry about is the fact that a hyperbola is a slightly different shape to a parabola, and it doesn't focus light from infinity to a point. Ritchie-Chrétien design is based on two mirrors, the primary and the secondary, and you need both mirrors to focus the light correctly. The Ritchie-Chrétien design has been around for quite a while. In fact, the last big telescope, the last large research telescope that didn't have a Ritchie-Chrétien design was the Hale 5-meter or 200-inch telescope. That was the last big telescope to use a parabolic mirror. At the time, Hale knew that the Ritchie-Chrétien design existed, and two hyperbolic mirrors in principle could give you less aberration than a single parabolic mirror, but Hale didn't want to go with something that was not tried and trusted. He wanted, because the 5-meter mirror was going to be the largest mirror cast up to that point, he didn't want to start experimenting with the design of hyperbolic mirrors, and it would have been much more difficult to grind and polish and test a hyperbolic mirror back in the 1930s. So he stuck with the parabolic design, which is fine for taking light from infinity and coming to a point, but not so good for aberrations when you're looking at a long way off axis. So for the Hubble Space Telescope, it was agreed parabolic mirrors have aberrations, therefore we're going to go with this Ritchie-Chrétien design of hyperbolic mirrors. I'm telling you this because of the main problem with a hyperbolic mirror is it's difficult to test on its own. You need two hyperbolic mirrors. And we said that in 1990 the Hubble Space Telescope was launched, and only when in orbit, when they started to take the first images, did the horror slowly dawn on those responsible for commissioning the telescope. They could not get it to focus. They moved the secondary mirror backwards and forwards. They allowed the whole assembly to cool down. They checked, they double checked, but they could not get the mirror to focus. They were expecting images such as the one on the left. What they were actually seeing was something akin to what's on the right there. Instead of getting what is essentially a pinpoint of light, strictly speaking it's not a pinpoint, it's a tiny disk, but instead of getting most of the light focused into that tiny disk, they were getting a reasonable chunk of it. 80 to 90% of the light was being focused into a small tight disk, but then they had this 20% or 10 or 20% of the light producing this horrible halo around every point source in the image. And they realised that they couldn't get rid of it. No matter what they did with the positioning of the secondary mirror, they could not get rid of this halo. It was eventually admitted that something was seriously wrong with the primary mirror. It was admitted that the mirror had spherical aberration. It had an aberration which should not have been present. Let's just make sure we understand what is meant by spherical aberration. I'm not going to talk about hyperbolic mirrors. Let's just pretend that we have a mirror here. Let's say it's a parabola that is supposed to take light and come to a perfect focus. So light from a distant object, an infinite distance off to the right hand side, should hit the mirror and come to a focus in front of the mirror. In spherical aberration, what that means is that light hitting a different part of the mirror does not come to the same focus. Perhaps you can see that in this particular case, the light hitting the outer parts of the mirror has come to a focus slightly ahead of the light that's come to a focus after hitting the middle of the mirror. And the further out you go from the center of the mirror, the worse the problem becomes. Any light hitting towards the edge of the mirror comes to a focus well before light hitting other parts of the mirror. This should simply not be the case. All of the light should have ultimately come to the correct focus once we'd taken the second mirror into account. So in this particular case, you can see that if you suffer from spherical aberration, you can place your detector, your CCD detector, at roughly where the smallest, if you like, circle of confusion lies, but you don't get all of the light focused at that point. If you move your detector to where most of the light is focused, from the center of the mirror, you can see the light from the edge of the mirror comes to a focus too early and ends up producing this horrible halo, this out of focus halo around most of the light focused in the middle there. That's how they recognized that this was spherical aberration. And that simply means it's called spherical aberration because spherical surfaces and spherical lens surfaces suffer from this same aberration. So they're not saying that the Hubble mirror was a sphere or the surface of a sphere. They're saying it was a hyperbola, but it suffered from this type of aberration, that light hitting different parts of the mirror came to a focus at different points. It's like having a focal length which depends on where you hit the mirror. So remember, what they were hoping for is something like what they saw at the bottom here. What they actually got was something like what's in the middle pane. And just for context, the top there shows you what you would expect for this same field of view of stars if you took that 2.4 meter diameter mirror in a telescope and took the same image from an Earth-based observatory. In other words, that top image has been deliberately degraded in resolution to give you an idea what the Earth's atmosphere would do. So yes, they have an aberration, but you could argue, well, even with that aberration, we're doing a little bit better than we would with the same telescope sitting at ground level, or sitting at the Earth's surface underneath the Earth's atmosphere. Well, okay, you're doing a little bit better than you would on the ground, but you've just spent $2.5 billion, or the euro equivalent, getting this into orbit in order to get 10 times the resolution. So there is clearly a problem, and the taxpayers will be furious unless you can do something about it. So what went wrong? How could you make such an abhorrent mistake as to grind a mirror but to make it the wrong shape? Tests carried out during the construction at Perkin-Elmer indicated that it was the most precisely figured mirror ever made. In other words, the surface roughness was about 10 nanometers, 10 billionths of a meter. And by surface roughness, I mean, roughly speaking, if you look at the smooth figure of the mirror, the mountains and valleys that would be in there, because no figure is completely perfect, the mountains and valleys would be of order 10 nanometers from one to the other, roughly speaking. And to put that into a little bit of perspective, if you think of 10 nanometer roughness over an object which is 2.5 meters or so in diameter, if you scale that up until the mirror is the size of the Earth, then the distance from the mountains to the valleys would be a few centimeters, about 30 millimeters or so. So if you can just mentally imagine the mirror the size of the Earth and then imagine the bumps being a few centimeters in size, you can see that it is indeed a very precisely figured mirror. However, it's very precisely figured to the wrong shape. They actually made it the wrong shape. It's off by about 2 microns, 2 millionths of a meter. And if that doesn't sound much, 2,000ths of a millimeter, remember that the wavelength of light is about half a micron or so, and so this is wrong by about 4 wavelengths of light, whereas of course you want a mirror such that light hitting any part of the mirror comes to a focus with an error of no more than a tiny fraction of the wavelength of light. You would like the surface of the mirror to be perfect to a 10th or a 20th or better of the wavelength of light, and here it's wrong by a massive 4 wavelengths of light. How did they make the mistake? Well, it all comes down to the fact that it's a parabolic mirror. It's not a parabolic mirror. If you had a parabolic mirror, you could simply take light from infinity and check that it comes to a perfect focus. With a hyperbolic mirror on its own doesn't focus the light. When it's in the telescope, it's going to be used in tandem with a second hyperbolic mirror. And you can't grind 2 mirrors at the same time and test them at the same time, because you don't know which one needs modifying or changing. So a hyperbolic mirror is tested with what's called a null corrector. It's an extra set of optics. It's usually a combination of mirrors and lenses. It's an extra set of optics in the test rig which is used to allow the hyperbolic mirror to be tested to check if it's focusing correctly. And the positioning of the optics in the test rig is absolutely crucial, and that is where they went wrong. One of the lenses in the null corrector was misplaced, and it was misplaced by about a millimeter from where it should have been. Different stories vary. Some say a washer was placed where it shouldn't have been, and that displaced the lens by a millimeter. Also, you hear that the positioning was checked with a laser, and the laser said that everything was perfectly in position, but unfortunately the laser was bouncing off the wrong surface and they weren't checking the correct distance. Whether the laser indicated that the washer was necessary, or whether the washer was in place and it wasn't noticed because the laser was bouncing off the wrong surface, I don't know, chicken and egg, which was the cause and which was the effect, but the bottom line was the test rig was not set up correctly, and because the test rig was incorrect, when they were then making the mirror to what they thought was the correct shape, they were actually grinding it very precisely to the wrong shape. A simpler test would have revealed the fault, but it was deemed unnecessary because Perkin-Elmer had done a very expensive and very extensive set of tests with their test rig, and they believed that their test rig was set up correctly, and therefore, although it was said, well, this is a very expensive mirror, if we spent a couple of £1,000 we can do a very simple test just to make sure everything is fine. Perkin-Elmer basically said, no, there's no need. We've just done a very sophisticated test and everything is A-OK. So the second test was never done. Of course, there is a backup mirror, and that was made and tested completely independently from Perkin-Elmer by Kodak, and so presumably didn't suffer from the same problem. However, the backup mirror is on the ground and the Perkin-Elmer mirror is sitting in the Space Telescope in orbit. What are you going to do about that? Well, there is one thing that saved the Hubble Space Telescope from a complete scientific and public relations disaster, and that was that it was designed to be serviced by the shuttle astronauts. So they then said, well, what can we do? Should we send up another shuttle and capture the Hubble Space Telescope and bring it back down to Earth and then start again? And take the old mirror out and go back to the Kodak one and check that one and test that one and put that one in and send it back up again? They decided that there was a simpler solution, and that is, sitting on the ground there was already a second camera. It is not unusual whenever you're sending things not just into orbit but across the solar system, it's not unusual to have a version that goes on the flight and a version that stays on the ground, which is essentially a duplicate which you can use to test out if things are not going to plan. You can see what's going on by testing the non-flight version sitting on the ground. So as well as having a camera up in the Hubble Space Telescope, they had a duplicate camera sitting on the ground. And they realised that what they can do, because the HST is designed to be serviced by astronauts, we can use the camera sitting on the ground. We can go back to Perkin-Elmer and find out exactly what went wrong. In other words, look at the test rig, measure how far it is off where it should be, and hence determine exactly what the error in the mirror is. Once we know what the error in the mirror is, we can modify this second camera sitting on the ground, and we can modify it by changing its optics such that it will focus perfectly. If you know the aberration of the primary mirror, you can insert corrective optics into the camera so that the camera will then work perfectly. And that's basically the plan they had. Modify camera number 2 and then send up camera number 2 on the next available shuttle flight. Well, a little bit later than that. That will fix the camera, but the Hubble Space Telescope is not simply a big telescope with a single camera, though we tend to think of it that way. It's actually multiple cameras and multiple spectrographs. So we can fix the camera on the ground, but what do we do about all the other instruments which are up there, which will have problems? For all of these other instruments, they decided to make a complex set of corrective optics, which they labelled CoStar. And they said what we're going to do is to put CoStar into one of the instrument bays. We're going to have to sacrifice one of the instruments that's already up there. We're just going to have to decide which is the one we can live without, and we'll replace it with CoStar. CoStar is a set of corrective optics. It's a sort of Swiss Army knife of mirrors. This is CoStar itself, which eventually came back to Earth, which I'll say shortly. But to give you an idea of what CoStar is actually doing, this little model on the right-hand side is perhaps more informative. There are a set of mirrors on different arms, which here are colour-coded, such that if you want to send the light to this particular instrument, this particular arm comes out with a small mirror on it, which is exactly the right shape to just correct for the aberrations in the primary mirror. And if you want to send the light to a different instrument, then a different arm comes out of the Swiss Army knife with a different mirror on it, and that will then send the light to this instrument. So if you've got 4 different instruments, you've got 4 different arms, and you can send the light to whichever instrument needs it, and those instruments will now have corrected light sent to them. So that was basically the plan. So just again a reminder that the HST is not simply one telescope with one camera. At any given time, the Hubble has got at least 2 cameras and 2 spectrographs on board. The actual type of camera and spectrograph keeps changing because the astronauts, the NASA astronauts, have visited the Hubble a few times, and the instruments have been swapped out, as we'll see shortly. So the actual telescope itself, I'll blow that up in just a moment, but just to point out for a point of sort of context, the cameras, which might be labelled wide angle or might be labelled high resolution, that depends on the focal length at which they work. And the nominal focal length of the Hubble is 58 metres. And the size of the chip in the camera is about this size here, a few centimetres in size. It's not that much bigger than the chip you probably have in your DSLR camera or possibly in your Astro camera. It is not a huge chip, but you're dealing with a focal length of 58 metres, which explains why the field of view of the Hubble Space Telescope is so relatively narrow. Let's just blow up that picture so we can see it a little more clearly. So this reinforces the fact that what we're dealing with here is a spacecraft with a telescope inside it. Notice that the telescope itself doesn't occupy most of the spacecraft. You see the front 1/4 or so of the spacecraft is essentially just a lens hood or mirror hood. There's the secondary mirror. The primary mirror is here. And so the primary mirror and the secondary mirror between them only occupy about half of the total cylinder that you can see. A lot of the space behind the mirror is taken up with the various instruments, whether they be spectrometers or cameras. And other instruments are built around the outside of the telescope, such as the optical equipment, the guidance, the gyros, and the systems that make sure everything is fed with power and everything is pointing in the direction that we want. So let's have a look at those service missions. I don't want to get too technical, but you can't really appreciate how the Hubble works without having some idea of the sophistication of some of the instruments that are on board. I'm not going to talk you through what all of these particular acronyms mean, but all we need to know is that WFC1 is the first camera. It actually stands for Wide Field Camera 1. That's the one that we know doesn't work, and the first thing that happened was Service Mission 1 replaced Camera 1 with Camera 2. Camera 2 was the one that was on the ground. It had the corrective optics fixed and then was sent up to replace Camera 1. The instrument that was sacrificed for COSTAR was this one. It happens to be a photometer. We don't have to worry about that. That photometer was brought back to Earth and was replaced with COSTAR. So now the Swiss Army knife should be able to send corrected light to each of the instruments on board. The little asterisk here is my little shorthand, meaning whilst the astronauts were there, they tweaked some of the systems. They tweaked the gyros to make sure the gyros, which are responsible for the pointing accuracy, they tweaked them to make sure they were working, and they tweaked some of the electrical subsystems to make sure that everything was on track. And they didn't do anything with these instruments down here. A few years later, Service Mission 2 didn't do anything for the first camera, but they replaced this item here. Roughly speaking, if you look at an acronym, if it ends with an S, it's probably a spectrometer or a spectrograph, and if it ends with a C, it's probably a camera. That's all we need to worry about. We don't have to worry about the subtleties between them. So on Service Mission 2 in 1997, one spectrometer was swapped out with a different type of spectrometer, and similarly this spectrometer was swapped out with another one. Why so soon after its launch on merely the second service mission would you completely swap out two spectrometers? Well, remember when the mirror was made, when the telescope itself was put together, we're talking about the 1980s. And it wasn't launched until 1990. So by 1997, technology has moved on. By 1997, the Hubble Space Telescope is already old in terms of the latest developments in cameras and in spectrographs. And so it was considered a good idea to replace these two spectrographs, and at the same time, these spectrographs were built with the corrective optics necessary to make sure they could work independently of the Swiss Army knife of the COSTAR. A third service mission was 1999. Again, a little tweak on the gyros, which fail every once in a while. And unfortunately, there was a little bit of a problem thereafter with this particular spectrometer. The grey indicates there was some sort of a problem. And in 2002 by the looks of it, Service Mission 3B tweaked some of the electronic systems, fixed the problem with that spectrometer, which was causing them some grief, and replaced what was the final instrument here, this faint object camera, with, okay, that breaks the trend, it looks like a spectrograph, no, it's another camera. They started, just to confuse matters, they changed the acronyms. Advanced Camera for Surveys, so it is actually a camera, replacing one camera for another. So by this time, in the early noughties, every piece of instrumentation has been swapped out such that the original errors in the primary mirror are no longer an issue. Now everything is functioning essentially perfectly. There were, however, a few problems. Things started to fail in the late noughties. There were some electrical problems. One of the spectrometers failed, the Advanced Camera for Surveys failed, and started giving them problems. In the early days, it was decided it was going to be very expensive to have a fifth service mission, and the 2009 service mission was in doubt. But eventually, the scientists, the astronomers, convinced NASA and ESA it is definitely worth having a final service mission to try and fix these little gremlins we've got, such that we can get the Hubble Space Telescope working as close to perfectly as we can get. So in 2009, they upgraded the camera yet again. The Wide Field Camera 2 had been operating, as you can see, for quite a long time. They replaced it with camera number 3. COSTAR is no longer needed. We don't need the Swiss Army knife of corrective optics anymore, because all of the instruments have been replaced with corrected versions of themselves. Therefore, the co-star could come back to Earth. That's the picture I showed you just a little while ago. And it was replaced with yet another spectrometer. So now we have 2 cameras and 3 spectrometers. Whilst the astronauts were there in the final service mission, they tweaked the gyros and the electronics, and they tried to make sure that all of the spectrometers and cameras were then working perfectly at that point, because the shuttle fleet was going to be retired and there was no possibility of other service missions. Now, in the past decade, I don't believe they've had any serious failures of the instruments. They've had problems with the gyros, and it could well be that the gyros are what are going to ultimately limit the life of Hubble. Even if the instruments are all working correctly, if you can't point at the object you're interested in and stay perfectly locked onto that using these gyro-stabilized pointing mechanisms, well, if you can't stay pointing at your object of interest, then it doesn't matter how good the camera or the spectrographs are. So let's hope the gyros do keep going for a few more years yet. So that's how it came to be where we are now, 30 or so years after the original launch. It took a few years to fix all the problems, but it's been running for more than 25 years now, producing wonderful images and spectra. So let's think about the legacy. How has it contributed to our understanding of the universe? There are, of course, far too many examples that I could possibly give, so I've just almost at random picked out a few that I think are worth mentioning. The distance scale, exoplanets, galaxies and supernova, and the age of the universe. I'll just touch for a few minutes on some of those aspects of what the Hubble Space Telescope has done for our understanding. One of the most important things it did was establish the size of the universe. Remember, when we're talking about distances, we can measure distances to close-by stars using parallax from the fact that the Earth's motion around the Sun allows us to get an idea from geometry of how far away the closest stars are. But when we want to go to stars, for instance here in the Andromeda Galaxy, we can't use parallax, it's simply too far away. We need a different rung on the distance ladder. And in this particular case, we're looking at the Andromeda Galaxy, and the Hubble Space Telescope has got the resolution to see individual stars in the Andromeda Galaxy, such that if you can identify some of them that are Cephids, these are stars whose luminosity varies over a particular period, and the period tells you the period is related to the luminosity. So if you can identify these stars, watch their luminosity change with time, by measuring that period, you know how luminous the star is. And if you know how bright it looks as well as how bright it is, then you know the distance to that particular star. And if the star is in the Andromeda Galaxy, that gives you the distance to the Andromeda Galaxy. And Hubble was able to measure a number of different Cephid stars within this galaxy, and hence determine quite accurately the distance to Andromeda, and that distance rung then allowed us to establish the distance ladder for much further objects, and hence established effectively the scale of the universe, which tells us about, for instance, given that we can use redshift to measure how fast galaxies are receding from us, if we can measure distance to more remote galaxies, then we have an idea of the Hubble expansion law, we have an idea of the expansion rate of the universe and the age of the universe. So Hubble was able to give us fundamental data such as the value of the Hubble constant, telling us the relationship between the speed at which galaxies are receding from us as a function of their distance. So it gave us a more accurate value of the Hubble constant and a more accurate value for the age of the universe. It was also a pioneering telescope in exoplanets. Since then, we've had more satellites going up and more ground-based telescopes dedicated to searching for exoplanets. But here in the early noughties, the Hubble Space Telescope imaged a planet going around the star Fomalhaut. You can see in this little inset here, there's an awful lot of light scattered from the central star, which has been removed from the image. But still, if you blow this particular inset up, you can see an object here which after 2 years has moved in its orbit around the star. This was one of the very first direct images of an exoplanet. There are less direct ways of determining the existence of exoplanets, such as the Kepler probe, for instance, looking at the dimming of stars when a planet moves in front of a star, but here Hubble has actually imaged exoplanets. Not only that, but it's been able to take spectra, again reinforcing the need for spectroscopy as well as imaging. An image can tell you what things look like, a spectrum can tell you what it's made of or what it's doing. And here Hubble has actually measured water abundance on exoplanets by looking at the absorption of light through the atmospheres of these various exoplanets, something that is very difficult to do with any other telescope. Of course, Hubble has looked at I don't know how many thousands of galaxies, which has given us a handle on how galaxies have formed. By looking back in time, by looking at more distant galaxies, we can look at galaxy formation early on in the universe, and with more local galaxies, we can look at galaxy formation more recently, and we can get the timeline of how galaxies have evolved over the last few billions of years, from shortly after the Big Bang to the present day. Various structures exist. I'm not going to go into the details of what we've learnt about various galaxies, but of course with thousands upon thousands of detailed images of various galaxies, it gives us an enormous amount of data with which to feed into the models we have of how galaxies evolve. One of the things that Hubble has been able to do because of its exquisite resolution is see detail that would otherwise be very difficult to image from the Earth. For instance, here we're seeing a galaxy amongst a whole load of other galaxies. What we're seeing are some of these orangey galaxies which are in the foreground of some of these bluer galaxies which are more remote. It's probably easier if I just show you this little diagram to give an idea of what's going on. Some of these orangey galaxies are in a big cluster which are sitting in between us on the left-hand side and a remote galaxy imaged from the right here. And because of the mass of all of the matter and probably dark matter in this galaxy cluster, the light from this distant galaxy is being bent or lensed as it goes through this galaxy cluster, which means this galaxy doesn't simply appear once in this image. This galaxy actually appears at different positions. And if I go back to the original image, this galaxy here also is imaged here, where I hope you can see the cursor, and it's almost also imaged up here as well. That is the same galaxy. But not only that, when we look in detail at this galaxy, we see what appears to be 4 supernovae going off at the same time. That seems incredibly unlikely, given that most galaxies only have a supernova going off once every 100 years or so. How lucky would we have to be to see 4 supernovae go off at the same time? It was quickly realised that what we're looking at here is another lensing event. This is one supernova where the light from the supernova is being lensed by a galaxy which is sitting right in front of the blue galaxy. This bright blob here is a galaxy almost perfectly lined up in our line of sight with the more distant galaxy, and as a result the supernova is being imaged 4 times. Not only that, but it was realised that, well, if we've got an idea of how this galaxy cluster is lensing the light from this distant galaxy and these distant supernova, then if we can get the theorists to work out how long each of these paths are, clearly the more direct route is going to be the shorter route, whereas the more indirect route the light could have taken is going to take slightly longer for that light to arrive. And so if we think about the light arriving from the galaxy up here, this particular version of it here, that light has taken a little bit longer to reach us. So if we can see the supernova going off in this insetted image, and we know that that other image in the top left is 6 months behind it or thereabouts, then we can expect to see a supernova go off in about 6 months' time. And therefore, for virtually the first time, we've had a heads up, we've had advance notice that a supernova is about to go off. Rather than catch a supernova after it started to get bright, just when we can start to see it, it's now possible to go to that galaxy and say, well, we expect a supernova to go off in 6 months. Let's start watching it in 5 months' time or 5.5 months' time, and we would expect to see it go off. And that's precisely what happened. The Hubble was told to go back to that galaxy and look at that particular version of the lensed galaxy, and indeed a few months later they did see the supernova go off, and they caught it in the very early stages, which is something you couldn't have done unless you've had this heads up of the different light through this galaxy cluster taking different lengths of time to reach us and allowing us to look back in time and cherry pick, let's look there and wait and we'll see the supernova going off. So a rather incredible result from the middle of the teenies, from about 2015 or so, I believe. Of course, the Hubble Deep Field is a classic that's been well advertised. The idea, you point at a patch of sky where you don't believe there's anything interesting going on whatsoever, and expose for about 10 days or so, about 1 million seconds, and then you find the image is full of thousands upon thousands of galaxies. There's perhaps 1 or 2 stars in this particular image. Every other blob you can see is a galaxy. And the field of view is quite small. If we look at this large rectangle here is the plate from a DSS, a digitized sky survey. Here's the moon for comparison, and the Hubble Deep Field is this red rectangle there. That's the size we're looking at, a tiny size compared to large survey images, and compared to the half-degree diameter of the full moon, you can see we're looking at only a few arc minutes of sky. And yet within that few arc minutes, here's another deep field. This was a slightly a different patch of sky. To make sure that we weren't looking in any special direction, another deep field was taken. This was called the Hubble Ultra Deep Field. Again, the same sort of field of view, but again, thousands of galaxies were imaged, and again, 1 or 2 or 3 stars in the same field of view. And because it's such a deep image, because it was such a long exposure, we're seeing some local galaxies, and we're seeing a great deal of galaxy further and further away, and hence we're seeing further and further back in time. This particular image went back, I think, something of order 13 billion years. The universe is 13.8 billion years old. This image has gone back to a redshift of something of order 7, 8, 9, back to distances, back to times of order 13 billion years ago. And that is unique as far as the abilities of the Hubble are concerned. Hubble has looked at a large number of galaxies and looked at a large number of galaxy clusters, especially of interest because of the lensing properties that I mentioned before. The mass of all of the objects in this cluster will bend the light from more distant objects, but in particular the amount of light that seems to be the amount of mass that seems to be bending the light here is more than can be accounted for by simply the luminous matter that we can see in these slightly yellowish galaxies, and hence we infer the existence of dark matter to account for images like that, in which the more distant galaxies, these blue streaks here that you can see, are very distorted galaxies, and some of them are stretched out into huge arcs. Some of these are very distant galaxies which have been distorted by the mass of the galaxy cluster, which must contain a large amount of dark matter in order to produce an image like that. So lots of Hubble images have been taken, which has extended our understanding of dark matter in the universe. In addition to its scientific legacy, the Hubble has managed to do something that most scientific instruments have failed to do. It's managed to touch the public consciousness. So when we look at something like the pillars of creation, a scientist will try and work out what's going on. The laws of physics have created these incredible structures, and Hubble has revealed them, it is said. Through all the research, the Hubble has brought the public along for the ride. It's taken the excitement that scientists feel with new discoveries and brought it home to non-scientists. That is something that is very rare. It's not the sort of thing that you find the Large Hadron Collider doing, for instance. Again, a very expensive instrument that is producing scientific advances, but it's not bringing the public along in the same way that the Hubble Space Telescope has managed to do. So let's take a look. Let's just indulge ourselves and look at some of the wonderful images that the Hubble has produced. And these are essentially just some of my favourite images. The Helix Nebula. Low down in the south in Aquarius, as seen from the UK, it's a very large nebula. I photographed it with a 300mm lens, for instance. That tells you just how large it is. It's about half the size of the full moon. So you can see from the Hubble's field of view that you would have to mosaic to obtain an image this large. But it gives, of course, wonderful detail of the structure within this particular planetary nebula. The antenna galaxies, the collision of two galaxies. The detail here tells us about star formation regions and what happens when two galaxies collide. That helps us understand galaxy evolution and indeed star formation. The Crab Nebula, I guess most of you are familiar with this, but of course the amount of detail that we could see in the Crab Nebula from the Hubble images surpassed what we could do up to that point. Mystic Mountain, not the Pillars of Creation, but a very similar looking structure, again imaged looking at hydrogen and oxygen and sulfur and coloured in much the same way, so it gives a similar appearance, but these are pillars of gas that have been sculpted by some very hot stars in the Eta Carina Nebula rather than in the Eagle Nebula. So this, if you like, is a southern hemisphere version of what we see from the northern hemisphere in the Eagle Nebula. But again, incredible structures brought home by using the Hubble palette to reveal the different chemistry that's going on inside these nebula. The Sombrero Galaxy, one of my favourite galaxies. Again, some amateurs might have tried to obtain an image of this, M104 in Virgo. I just thought it was beautiful to see this dust in the disk plane, a very large diffuse central bulge, but the contrasting with the dust around the edge just gives a beautiful effect. The globular cluster M5, this is not only a wonderful image in its own right, it reminds us that when you try and image globular clusters, especially from the ground, the densest part of the globular cluster, seen on the left-hand side of this image, the stars are so dense it's sometimes difficult to actually resolve individual stars. And so to actually study the stars in a globular cluster, a lot of other telescopes would have to resort to looking at the outer part of the globular cluster where the stars are far enough apart that they could all be resolved. Whereas the Hubble Space Telescope has the resolution to look not only at the outer part of the cluster, but all the way into the core of the cluster and still resolve those tightly packed stars. Something that would be very difficult for other telescopes. A beautiful barred spiral galaxy. It's thought that the Milky Way is a barred spiral, but I'm sure the bar doesn't look quite as dramatic as this one, where the bar is almost as long as the individual spiral arms. Quite a wonderful sight. The Rose galaxies, another example of interacting galaxies, where in this case it looks like a spiral galaxy has been disrupted by the presence of the galaxy below, which is also getting distorted. And again, looking at lots of images like this help us understand galaxy interactions and help us understand galaxy evolution. The Veil Nebula, which again is a very popular target with a lot of amateur astronomers, by taking images at multiple wavelengths. I can't remember how many there are in here. I think there are possibly 5 different wavelengths, hydrogen, sulfur, oxygen, and I can't remember what the other elements are. But by taking images at different wavelengths corresponding to different elements and then combining them into a colour image, you can get an idea of the extraordinary structure within this particular supernova remnant, which again gives us more information about how stars live and particularly how stars die. The Pillars of Creation, I guess I couldn't not show that. This was the 25th anniversary photograph. The Pillars of Creation were taken early on in the Hubble's life, but when the camera was finally replaced with camera number 3 with a slightly larger chip and a higher resolution, that's the one that I was showing you earlier, that's the size of the chip in camera number 3, 4 centimeters by 4 centimeters, a resolution of 4000 by 4000, so 16 megapixels. Not particularly high compared to whatever you've got in your digital SLR camera, probably, but again, a reminder that you don't need a huge CCD to get fantastic images. It depends on the quality of the optics to give you these sorts of images. So that was the 25th anniversary image of the Pillars of Creation in the Eagle Nebula. And again, just returning to the Hubble Deep Field, a reminder that this is not only an iconic image, it also tells us a huge amount about the science, because we've got thousands of galaxies at different distances which we can then study to give us an idea of how the universe has evolved. And of also, it's incredibly humbling simply to look at that and to remind ourselves that we're not looking at a star field. Apart from a couple of stars, 3 stars I think in this case, we're looking at thousands upon thousands of galaxies going all the way back to the very early part of the universe. Not quite back to the Big Bang, but we're looking most of the way there. So what lies beyond? Ground-based telescopes, as I'm sure you know, now have the option of having adaptive optics. In other words, you can correct, to some extent, for the turbulence of the Earth's atmosphere. You can shine a laser into the upper atmosphere, which produces an artificial star high in the atmosphere, and if you look at that artificial star and see how it's shimmering, you can get an idea of how the Earth's atmosphere is moving, and if you can quickly enough move your mirrors, you can actually compensate for that and basically take out some of that turbulence of the atmosphere. So if you can use adaptive optics on Earth-based large telescopes, is there still any need for a space telescope? Well, there is a fundamental problem with using adaptive optics by shining an artificial star into the sky. You can shine it into the sky and you can get an idea of how the Earth's atmosphere is turbulent in the region of the artificial star. But over there, it's going to be turbulent and chaotic, and it's not going to be the same. And over here, it's not going to be the same. So you can correct for the Earth's turbulence, but only over a limited field of view. So despite the fact that we've got these huge telescopes like the 30-metre and the 40-metre coming online, which will be using adaptive optics, they can only achieve the best resolution over a limited field of view, whereas of course a space-based telescope, providing you get the optics right, have that resolution over the entire field of view of the CCD. It's not limited to just looking at one exoplanet or one star system close to the centre of the chip. They can get that resolution over the entire chip. So that's how adaptive optics differs from putting a telescope into space. Let's just have a quick look at other space-based telescopes. So Kepler, again, I guess you probably already know this, Kepler had a very specific mission to find Earth-like planets orbiting other stars. And it did that with a relatively modest size mirror, but it had a very large camera. So in other words, there's the CCD, it's almost a coffee table sized detector. And that detector was not scanning over the entire sky. Kepler simply stared at one patch of sky and simply recorded the intensity of the stars over and over and over and over again, looking for any characteristic dip in the intensity of a star, which tells you that an exoplanet has transited the star and has made the star light dim. And for those that know your constellations, I think you can see that we've got Cygnus down here and Vega and Lyra over there. So you can see the patch of sky that it was looking at. And basically it just stared at that patch of sky, looked at a very large number of stars and just kept recording for years to find as many exoplanets as possible. And at the end of the day it found, I can't remember what the number is at the moment, but something of order 5,000 or so exoplanets. Gaia is an ESA mission which had a very ambitious set of aims and is still delivering on those. It was going to be measuring the positions of not a few thousand, not a few million, but something of order 1 billion stars, and to measure the positions of those stars accurate, again, not to arc seconds or milliarc seconds, but to accuracy of order 25 micro arc seconds. And it was going to perform a limited set of spectral and photometric intensity measurements. And with all of that information, the positions of the stars, the brightness of the stars, and ideally some information about the colour of those stars, it would be able to work out, by remeasuring these positions over and over again, it would be able to work out how much the stars are moving, and hence produce star velocities within the Milky Way to generate a complete three-dimensional map of what the stars are doing in the Milky Way, or at least what a billion stars are doing in the Milky Way. Not all of them by any means, but a very good representative set which would give us a much better idea of the dynamics of the Milky Way. How does it get that sort of resolution? Again, it's not a particularly large mirror. It gets that accuracy by making repeated measurements over and over and over again. And the more measurements you take, the more accurately you can pin down the positions of the stars. And by repeating the measurements week by week, month by month, year by year, you can get the proper motions and velocities of these various stars. And the data releases of Gaia will be coming out on a yearly basis from now on. So, reflecting again on the Hubble Space Telescope, if you'll excuse the pun of reflecting on the Hubble Space Telescope, is there a successor waiting in the wings? And again, I'm pretty sure you know the answer to that. The James Webb Space Telescope, which should be launched fairly soon now. I know I've been saying that for the last 10 years, but now it's true. It will be launched fairly soon, hopefully within the next 6 or 7 months. It should be launched, and within the year it should be parked and ready to take data in principle. You can see the size of the James Webb mirror compared to the size of the Hubble mirror. The Hubble mirror diameter 2.4, made of one slab of glass. The James Webb, you can see, is segmented and is going to be nominally about 6 meters or so in diameter. Strictly, you can't talk about a diameter when it's not a circle, but you know what I mean. You can see it's substantially larger, much larger surface area, in principle a higher resolution as well. The James Webb is not going to be placed in Earth orbit, so the Hubble Space Telescope is just a few hundred kilometers above our heads. The James Webb, by comparison, rather than being in Earth orbit, is going to be sent to what is called the L2. There are a number of these so-called Lagrangian points labelled L1 to L5. These Lagrangian points are points relative to the position of the Earth in its orbit around the Sun, where if you place a spacecraft there, it will stay put. In other words, it won't be pulled into the Sun, it won't be pulled into the Earth. You might need a tiny amount of station keeping, but on the whole, if you place an object at these points, it'll stay there. And so, for instance, Gaia is currently placed close to L2 rather than positioning it at L2. It's actually a little bit easier just to put it in orbit around L2. Not quite as large an orbit as is shown there, but L2 is about 1 million miles away from the Earth, so substantially further than the Moon, for instance. Why would you leave the Hubble Space Telescope in orbit around the Earth but put the James Webb at such an inconvenient place 1 million miles away from Earth? Well, the James Webb is going to work in the infrared and the Earth is hot. Therefore, the Earth will be producing a lot of infrared radiation, and the James Webb is being sent as far away from Earth as possible. The image I showed you previously indicates it's got a very large sun shield. That's going to shield it from the sun and from the radiation from the Earth. And of course, when it's out at L2, even if we had a shuttle fleet, it would be essentially impossible for the shuttle to reach that far, 1 million miles away from Earth. So there is no way to maintain the James Webb. So it's going to be sent to L2 while it's on its way. It's going to have its sun shield unfurled. The mirror is going to unfurl. It has to be sort of packaged up, small enough to actually be put into the nose of a rocket fairing. Then it's going to unfurl itself and unwrap itself. Hopefully that will go without a hitch, and when it gets to L2 it'll park itself there. It'll say hi to Gaia, and I'm sure they'll agree to coexist close to the L2 point. But if anything goes wrong, there is no way of going out to fix it, and there's essentially no way to bring the James Webb back to Earth if anything goes wrong. Which is one of the reasons they've been so careful to try and make sure the James Webb is going to work when it actually gets there, because unlike the Hubble, there can be no second chance. So what will the James Webb do that the Hubble couldn't do? Well, it'll work in the infrared. That's the main difference. And so in some cases it'll see more than the Hubble. So for instance, on the left there is a Hubble picture of the Eagle Nebula looking at the pillars of creation. And that gives us an idea of those gas pillars that are being sculpted by stars, but we can't really see inside those gas pillars. Well, we can to some extent, because the Hubble, although it often works in the visible part of the spectrum, it can be pushed a little bit into the infrared. So for some of its life, Hubble has been working in the infrared, and the picture on the right just shows you what a difference it makes. You suddenly see loads more stars. They were there anyway, but of course the nebula was making them difficult to see. And in particular, looking inside those gaseous pillars, we can now see that they're a little more transparent. We can start to see what's going on inside, simply because of the longer wavelengths of infrared radiation. So if we want to see what's going on inside a nebula, if we want to see what's going on around the dusty environment of a star that's starting to have planets born around that star, it's very difficult to see in the visible, but the infrared will cut through a lot of the dust, a lot of the gas, and will allow us to look inside. That's one of the reasons that James Webb will allow us to see more than the Hubble. A second reason is that when we're looking back in time, remember the iconic Hubble Deep Field images, some of those galaxies are a very long way away. They are billions of light years distant. They might be receding from us at more than the speed of light, and some of those wavelengths of the light from those galaxies has been redshifted, and although some of the light will be redshifted perhaps from the ultraviolet into the visible, quite a substantial amount of light is going to be redshifted from the visible part of the spectrum into the infrared. So very distant galaxies that are moving away from us faster than light are going to be more and more difficult to see with the visible part of the spectrum because there's so little light to catch. Whereas in the infrared they would be expected to be brighter simply because their recession velocity has pushed a lot of their light into the infrared part of the spectrum. So it's hoped that when the James Webb does the equivalent of the Hubble Deep Field, when it does the James Webb Deep Field, it will be able to see the galaxies as brighter objects, and hopefully it will be able to see further back in time than the Hubble is able to do, just a little bit closer to the Big Bang. So I've told you about why we need space telescopes and a little bit about ground-based alternatives. I've given you the history of why the mirror was flawed and how they fixed the problem. I've talked a little bit about some elements of the science that Hubble has been able to deliver for us and how the public was along for the ride. And I finished with looking at, yes, despite the fact that ground-based alternatives will have adaptive optics and will come an awful long way, there is still a need for space telescopes. Thank you all for listening.